thank you all, and thank you, Randy. I appreciate the opportunity. I think you keep it pretty informal. I mean, people have questions during. I much prefer that, so I'll try to keep it in the time limit. So this is just a rough outline for the presentation. I want to talk some about, the global sanitation crisis. Randy did a good job of introducing it. I'll give some background, but also some background on what the Gates Foundation is doing broadly in that space. And it's good to see some people from Mark DeSchuss's team here who are involved in a sister project in that, and we have a lot of collaborations already going with that group. And then I'll talk some about the new center that we formed, and it's really around partnerships and innovation, partnerships in WaSH. I'll give a couple of examples of some projects that we have ongoing, and then segue into user perspective, sort of non-engineering aspects and issues that we're trying to address that relate to adoption, and possibly some opportunities to collaborate. So the sanitation crisis, as Randy indicated, a lot of people know this stat. There are roughly 40% of the world's population that either practice open defecation or don't have access to safe and effective sanitation. More people die from poor sanitation and diarrheal disease and AIDS and malaria combined. But what is less commonly known is about another 30+% of the world's population, they have access to sewage, but there's something wrong with that system. A lot of that sludge still ends up in the drinking water. And we refer to that as sort of institutional open defecation. So this was a study that was done by WSP. It was a 12-city review that looked at sources of defecation. So what systems exist? You have your sort of WC to sewer. In a lot of the developing world, what this really means is you flush it and it goes from affluent areas to less affluent areas. You have sort of on-site facilities, and this could be pit latrines or some form of on-site waste treatment. Pit latrine fills up, sometimes it's empty, sometimes it's not, and then there's open defecation. You kind of go along, if you look at the sort of local environment, the WC to sewer, you flush it, it goes away. It does what it's supposed to do, at least at that stage. And then you have your on-site facility, and then you have your open defecation. What we see, and this is a worst case, this is looking at Dhaka in Bangladesh, but what you then see in the systems, especially in stress systems where you've had sewage systems that were developed 10, 20, 30 years ago, and populations have increased by a factor of 5 to 10, you see stressage in the system. So you either see leakage in the pipes, or in the cases of on-site waste treatment, pit latrines are just left to overflow, or they just go and they build another pit latrine, and it's just you have seepage into the groundwater. Even in cases where you have businesses that come along and they empty the pit latrines, where do you think they take that sludge? They take it to a convenient place to dump. A lot of times it's in rivers and streams. You have illegal dumping. Then what you have, because of overcapacity, even the central waste treatment systems, in some cases they're overflow, or you just have ineffective treatment. And so in this case, maybe only 2% of that waste ends up being treated. So the issue becomes more of that of fecal sludge management, and not just open defecation. There's a lot of energy around trying to change behaviors around open defecation, but this is a broader institutional problem. And so the Gates Foundation program is aimed at trying to figure out how do we better manage the entire process. And if we look at everything from sort of on-site treatment to safe transport to community processing, how do we create value at every step along the way? And the Gates Foundation WaSH program spent a lot of time thinking about how do we give sludge some value? They call it the sanitation value chain. One of those is how do we safely, extract, empty the pits, and then transport it someplace so it can be processed safely? How do we create a central processing facility that turns sludge into something that has some value? It could be energy, it could be water, it could be an agricultural supplement. And then there's a Reinvent the Toilet program. And so a lot of the projects that I've been involved in through the Reinvent the Toilet project and the Phase 3 effort is on-site waste treatment. How do we effectively treat the waste at the point of deposit in a way so that whatever is discharged is environmentally safe? And this is kind of fun. I think some of those who have been involved in the project, but anyone have any idea who's credited with the invention of the modern day toilet?
Thomas Jefferson.
Hmm?
I just made that up.
Thomas Jefferson.
Oh, Thomas Jefferson. Oh, that's interesting. Look at my timeline. Any ideas? You know, a lot of people associate Thomas Crapper with that. You know, he was involved in the whole, you know, bringing toilets from the fields into the home. But it was John Harrington in the court of Queen Elizabeth I that was credited with the original flush toilet. It was loud, which is why Queen Elizabeth didn't like it, and she chose to go with the more traditional chamber pots. But in late 1500s, it was John Harrington. And there's a local cartoon about that. I think I forget. But anyway, about 200 years later, Alexander Cummings took out a patent on the S-trap. And so it was about 200 years between the first flush toilet to someone saying, hey, we need to do something about the odor. And the S-trap, you know, that created this water gap that kept the sewer gases that were accumulated down here from making their way up into the chamber room. And then Thomas Crapper came in. Industrial Revolution caused a lot of people to move to the cities. Toilets moved from outside to inside. And they really did refer to this as the Crapper, Thomas Crapper. And then about 200, or a little over 100 years later, the Gates Foundation in 2010 launched their Reinvent the Toilet program. And so this is 200 years from the original flush toilet to, you know, how do we change the paradigm from we flush it, it goes away, someone else treats it. How do we sort of take everything that's in that waste, create some energy, create something that has some value, and treat it safely on site? This is interesting because it shows the investments in just the technology. So the entire water sanitation and hygiene group has a lot of other programs, but what this shows is, you know, in 2010 they launched the Reinvent the Toilet Challenge. They funded their first series of grants in 2011. In 2012 they had about $18 million that were going into new technologies. And then that increased every year, and then, you know, next year is projected to be a little over $60 million that are going into new technologies. Just last year, we had a 5-year anniversary of this program. They've invested a little over $200 million in technologies to reinvent or change the way in which we process waste over the last 5 years. And as Brandy alluded to, we received about $11 million in grants here at Duke to establish what we're referring to as the Center for WaSH. But it's focused on technology transition and how do we fill strategic technology gaps that can impact the broader water sanitation hygiene portfolio at the Gates Foundation. And another key aspect of it, and really the reason that these programs are at Duke is all of these require a multidisciplinary approach. It's not good enough just to have an engineering-centric design. You need to have an understanding of what the users and other stakeholders in the system require. So, Center for WaSH, Water Sanitation, Hygiene, and Infectious Disease. I'm going to talk about 3 programs that kind of form the anchor for that center: the Reinvent the Toilet Phase 3, the Sanitation Technology Cluster, and then a new opportunity that's a Sanitation Technology Accelerator program. Reinvent the Toilet Phase 3, we're 5 years into a program, and it's focused on prototype development. We've already done the laboratory demonstration. It's all now about getting prototypes out into the field, testing them in realistic conditions where you're stressing them in environments that they're likely to see out in the field. What are the failure modes? You know, what are the operational costs? You know, we can test them in the lab. We know how much they cost. We know how they behave. Once real users have access to them, you know, how are they perform? How do they function? And then how do we then, based upon those data, develop a process robustness? Then the user data. I mean, without the users, I mean, it's one thing to have a technology that works, but do they care about it? We're recycling water. Do they care about that? How do they feel about that? How do they feel about the safety, the security, the environment of the toilet? We're no longer, when we talk about reinventing the toilet, we think of that porcelain thing that we interact with when we go to the bathroom. What we have is a self-contained waste treatment system right under, beside, or adjacent to that. How do people feel about that? How do they feel about what's being processed, what's being recycled, and how it comes in contact with your body? And then there's partnerships around product development. A lot of the next 2 years will be developing the manufacturing partnerships, the prototyping partnerships, and then even the customer partnerships that will form the basis for a successful product that comes out of this. We're taking it to 2 locations, one in Coimbatore, India, and one in Durban, South Africa. And these are 2 different use cases. These will happen in 2018. First quarter of 2018, we'll be setting up in Coimbatore, and then the second quarter of 2018, outside of a township outside of Durban in South Africa. The use case in Coimbatore is really specific. We're interested in women users. We did a lot of studies that looked at thresholds to adoption, and men don't care as much where, when, how, and why they use the bathroom. Women, especially in a lot of developing nations, have more limits on where they can go, when they can go, how they can go. So and plus, just the issues around menstrual hygiene disposal. How do we create an environment? We already have a new technology that's treating waste. How do we create an environment that's attractive to women and girls? And so this is a mill site, a textile mill outside of Coimbatore, and it has between 10 and 30 users, and these are women who come from more rural settings. They come into the city, they work for a couple of years, and then they go home. They actually live in a dormitory style. They work adjacent to the dormitories. And so we're taking our prototype and we're retrofitting one of the toilet stalls at that site. And then there's a township outside of Durban, and this is more of a family setting, male, female users, families with children. It's a container-based system. Typically, this will have between 2 and 4 toilet stalls. It will also have showers. It will have sinks. And so here we're studying the broader community-style usage. Then there's the Sanitation Technology Cluster. And so this was a pilot. It was kind of an experiment that the Gates Foundation tried. And they've already funded a lot of these projects to develop new prototypes, to develop new systems. But many of them are using similar technologies. Many of them are using a certain type of disinfection technology. Many of them are using some form of dewatering or separation technology. Many of them are using, let's say, a combustion or a thermal process to treat the solid waste. The question was, can we pull some of these people under the same tent and get them to work on common issues that exist across the grantee portfolio? And so they piloted this, and this was launched this year at Duke, and it's funded to about $2 million a year, between 10 and 12 projects each year, to look at everything from, is there fundamental science that can be gleaned that can impact the broader portfolio, broader understanding of disinfection, broader understanding of the properties of fecal sludge. Are there enabling components or enabling technologies that if we just had a better dewatering system, it could make our toilet, it can make someone else's toilet that much better. And then are there some high risk concepts that it really doesn't make sense to fund a single entity to develop it for a single technology, but let's put it into this portfolio and let's kick it around a little bit. And if it does, most of these are going to fail, but some of them, if they're successful, then how do we figure out how to get them into the larger portfolio? Then, another part of it is most of their grantee portfolio are academic institutions like ours. But as we know, research universities are really good at getting technologies up to a certain stage, getting to that laboratory demonstration. part of our sweet spot. But not all universities like ours are good at getting products out into the field. So part of the sort of goals and objectives are to identify industry partners who can work with these university teams to transition to technology. We even have internships that we sponsor that'll have students from university going and working at the companies, and then the companies coming back and advising the students, so there's more integration and better transition of the processes. And then the cross-cutting elements. What are the users telling us? We talk about engineering being really cool, and that's but what if the users don't like it? They don't like the way it smells. If they don't like the way it looks. So what are the users telling us? So we have a number of these cross-cutting themes. Gender-centered design. If we want to focus on the needs of women and girls, let's go and let's design, let's engineer a system that's aimed at solving the priorities for women and girls. Let's not build a system, put it out in the field, and then they say, okay, retrofit it so that it's attractive to women and girls. Let's actually create that into an early feedback loop so that the engineers are working with the people who understand the users. And so each year we'll fund 1 to 2 either master's students or teams of students to look at some of these cross-cutting themes that cut across the technology portfolio, feedback into the engineering teams to help improve the process. And so I talked about, we talk about the 3 legs of the stool on which the engineering sits or the technology sits. It could be, sociological. There could be a religious bias. There could be a cultural bias. There could be sort of a historical bias. Like, a lot of these communities have what's called NGO fatigue. They've been studied to death. They've had, a new NGO comes in, delivers a new technology that's going to solve all of their waste treatment needs. And then in 2 years, what happens? They leave. They go away, they write the reports, and then a new one comes in. We've heard this when we've gone into the communities and they've talked about, when we talk about what their needs are, and one of the first things they might bring up is, this other group that brought this other thing in there and how what we're doing is different. So, how does that sort of historical bias influence their willingness to accept this new technology? Political, what's the policy and regulatory landscape that will impact whether or not this new technology will be successful. And then there are the economic constraints. How much does it cost? Is it affordable? What are the existing business models? We're bringing a new technology into a community. There's really not an existing market. So what are the existing business models for anything like this that we can mold into? We want to be as, we want to minimize how different we are from the existing ecosystem, the existing landscape. Okay, and then the last project is what we're calling the Sanitation Technology Accelerator. And this was kind of an interesting question, and it came up through some discussions that we were having at one of our program reviews. And it was really around, we have all these great technologies that we've brought up to, we've developed a lot of great technologies. Why don't we have a lot of great or successful products? And the classic valley of death question. There are a lot of companies, there are a lot of programs that are very good at generating innovations and new technologies. But then it's called the valley of death because it's a very different process to get technologies from demonstration to product. And so we received a grant to essentially ask the question, can we leverage other mechanisms out there to more successfully transition these technologies from lab to product? What if the Gates Foundation were to put in a certain amount of money each year? Can we use that money and leverage it against other funding mechanisms? Either funding to develop more technologies, that's the sort of brute force, increase the pipeline, or can we leverage it with, let's say, venture capitalists, impact investors, the Duke Startup Challenges. What if we were to sponsor, 5 new Duke Startup Challenges in the sanitation space next year? How could we better use these funds to accelerate product development from lab demonstration out into successful commercial products? And so, basically, what government funding exists right now that's funding projects in the sanitation space? And can we leverage it? Can we say, if we come to you with this funding from the Gates Foundation, will that help us Can they add to it? Can we leverage those technologies? Are there technologies that they're developing now that may not be for the developing world, but if we move it into our portfolio, we can benefit from that? And we're working with NASA, and this is the group that creates toilets for space station. It costs about $50,000 to take a liter of water into space. And so they've become very good at recycling and reuse of liquid waste. We send an intern out there every year because there's got to be something that we can learn from their 50 years of getting, supporting astronauts in space. The Army has programs for forward operating bases. About 60% of all injuries in Afghanistan and Iraq are associated with supply chain. So if you can reduce the amount of water, the amount of fuel, and the amount of waste that you have to backhaul, you can directly correlate that with fewer injuries. So they're already funding technologies for, let's say, resource-starved environments. We just don't think of it. I mean, the companies and the people who are working on those programs may not be the same ones that are working on the Gates Foundation programs. Can we bring them into the same tent and figure out how to leverage those technologies? And basically, where in this gap can we have the greatest bang for our buck? If the Gates Foundation is willing to put some money in, do we say we just need more things on this side, and therefore that'll give us more things that make it through this valley of death? Do we need to create some support structure in this valley of death so that new technologies have a better chance of making it through? So coming out of this grant, our deliverable is really a proposal for 2 to 3 projects where we've identified opportunities to leverage new funding or sort of say new commercial opportunities on the product side, and those will go in sometime in 2018. And this is just an example. We already talked about our existing Center for WaSH Aid. This is an 8-year, they put about $20 million into new technologies, and then there are a number of other projects that we're involved in that are also developing technologies. But the question is, within this Sanitation Technology Accelerator, what are some of the core capabilities that, if you had access to that as a research facility, if you had access to better prototyping facilities, better access to capital, better value engineering, meaning, I have this widget that we built in our labs here at Duke. I now want to develop it for India. Can we value engineer it, or can we figure out how to build it in India? And then are there resources that help us to develop the business case, the economic analysis required to determine whether or not this is going to be a successful product? So, we want to get things from lab prototype to field prototype, ultimately to commercial products. And what this kind of looks like is, or what it's shaping up to be is, the Gates Foundation is willing to put in about this much per year. We want to be able to leverage it against these other funders of innovative technologies in the WaSH space. And these are people we've talked to, and it's interesting when when you go to a program officer and say, I have this pot of money that I can add to if you're willing to put in, they love that because you've helped them buy down their risk. They love, and even programs within the Army, they have a special pool where if a third party puts in money, they can actually match that up to a certain amount. And so there are a lot of opportunities to do this instead of just sort of creating the right mechanism and the right support structure to be able to transition that through. And then there are opportunities on the other side. Are there investment corporations that when a product gets to a certain level of maturity that we can pull it in? Are there startup challenges? It's low-hanging. It would be an easy, let's say, test case to say, let's create 5 new, we'll sponsor 5 successful projects through the Duke Startup Challenge next year in the sanitation space, and let's just see what comes out of that. And there are other, NASA has a patent portfolio, and for small businesses that want to in-license technology, they have either 0 or very low special rates for businesses that want to license in technology that's been developed at NASA for the purpose of commercializing new products. Didn't know that, but can we leverage all of these as part of our technology accelerator? Okay, let me now switch to a case study. So this is one of the examples of our let's say Reinvent the Toilet system, and I really want to highlight the value of having multiple expertise coming together to solve a fairly complex issue. This is a schematic of our toilet system as it exists now. Just fundamentally, you have this system was developed from India, so you have a squat plate. This is our point of deposit. All the waste goes in here, and then it goes to a solid liquid separator. Solids, for the most part, go in this direction. Liquids, for the most part, go in this direction. The solids go through kind of a homogenization process. They're not all equal, so we like to have something that's fairly consistent. And then it goes into a drying process. From that, feces is about 75 to 80% liquid water. We want to dry that. We want to remove the liquid. And now we have a combustible fuel that creates a thermal energy, some electrical energy. That thermal energy is then used to dry the next batch of, let's say, incoming products. On the liquid side, it goes to, this is very similar if you ever had a septic tank. This is just a multi-stage settling tank that allows the, let's say, suspended solids to settle out. And then it goes into a disinfection module, and here we use electrochemical processes where you're essentially taking the salts, the natural salts that exist in urine, and you're converting that into chlorine and other oxidants that break down the organics and destroy the pathogens in the liquid. That's stored here, and then some of that is recycled back through for flush. Any excess is discharged. It's been safely disinfected, and then it's discharged. Okay, so the electrochemical process, that's the heart of this liquid treatment. When we first proposed this program, we said, okay, we understand electrochemistry, we know how this works, we can use it to destroy the pathogens, we can use it to break down the organics. Great, problem solved. The problem is it's kind of energy intensive, 65 to 100 kilojoules per liter. When you're in a resource-starved environment that may or may not have access to regular electricity, that can become a problem. But we could still disinfect it, and we met the criteria for the Reinvent the Toilet program. But this is what disinfected liquid looks like. What do you think? This is where, and so Miles Ellis, who runs our field programs, was calling us up and saying, it's disinfected, the lab says it's fine, it's safe to discharge, but this is what it looks like. Do we need to change the color of the bowls so that, this doesn't contrast as much? We were considering everything like that, but this is why this is why as soon as you have something that's ready for users to use, you take it out there, you test it, it's real material. And what we then had to do is say, okay, we're electrochemists, we understand the processes, we're just going to brute force it, and we're going to just, run the electrochemical process until we get something that the users accept. And we can do that. And you get something that looks like this. And the users started using it again, they didn't complain as much, and everyone was happy. The problem is it costs about 10 times as much energy to achieve that. And so that got us thinking. We started, that's where the scientists, someone who had nothing to do with the electrochemical process started looking at it and saying, how can we break this down mechanistically into the fundamental processes that allow me to achieve the goals that I need? And so we're engineers, we're like, all we really cared about was the right side of this. We want to treat everything so that it's safe, using as little energy as possible. And then you have the users over here saying that's fine, but I care about odor, I care about color, I care about turbidity. Is it foggy? Does it look strange at all? Because you're already asking me to use something new. So they care about what the environment is. So what we did is, if you have that one tool, which is an electrochemical process, you can use it to treat everything. And we were able to do that. But, it's not always the optimum way to go. And so this is a process, I actually have a curve like this on my whiteboard. It's like almost every process in nature has a window over which the efficiency is ideal. And then to the left and to the right of that, it's not. And so if we only have one tool, we're trying to treat from here to here. You know, this is an arbitrary process range. It might be, you know, percent dissolved organic. You know, I want to take it from here all the way down to here. But the tool that I have is only efficient over this range, which means I'm being very inefficient here and very inefficient here. What if I combine it with other processes? I have other tools in my box. You know, maybe they're shifted a little bit. You know, if you start thinking about using a combination of processes over the range in which they're more ideal, more optimum, that's the whole concept behind a hybrid approach. You know, let's not just brute force it and use the one thing we know. Once we understand mechanistically what we're trying to change, then we can say what are the processes that are most ideal for that outcome. And so now let's go back at our sort of reusable water mechanism breakdown. If we want to destroy pathogens, great. You know, electrochemistry really is, you know, the best for that, you know, in the tools that we have at our disposal. Well, let's reserve that for when we absolutely need it, because that's the most energy intensive. Are there other approaches that we can use that don't cost a lot of energy? You know, redesign your tank so that the suspended solids, we call these sort of the floaties, that if you give them enough time, they settle out, right? Let's just do that. Let's just let those settle out. And then you have the dissolved solids. You know, what are some other technologies, lower energy intensive technologies that could be used? Activated carbon has been around for a long time. We actually did that in collaboration with Aaron and Mark DeSchuss's group, who's already using that as part of his system. We said, okay, what would happen if we added that to either the front or the back end of our process? Could we use that to improve the overall process efficiency? And so this kind of provides the rationale for that. Let's reserve the energy-intensive process, the electrochemical process, for where it's absolutely needed, and let's use low-energy processes to treat the rest. This is the team, and it started off with a cluster of like 3 or 4, but then the folks at the Gates Foundation says, let me just take everyone that's working in liquid disinfection or liquid treatment, and let's heap them, or let's lump them into a single program in hopes that there's some hybrid combinations that will emerge from this that would give us a portfolio of options to address multiple scenarios. And so this, I'm not going to go through what everyone's doing, but you can see it there. And we set up a number of test beds. We set up a test facility at RTI. We had some interns working at NASA that summer. They had a lot of experience working with activated carbon through their space programs. We had 2 of the interns set up a stack of activated carbon and then electrochemical processing at NASA. In this case, it's a triple system, and they looked at 2 different modes of treatment. And then we also connected it to our field system at CEP University in India. And so let me just go through the results. So remember, disinfection only, you know, lower energy, but look like this. You know, about 10 times more energy to treat it to the point where the users said, okay, I'll go back in there and I'll use it again. And then we install the activated carbon stack. So less than half of the energy that it took to get the dirty brown stuff, and it's much cleaner. It's cleaner, it smells better, even has a little bit of residual chlorine in there that the users like because they associate chlorine with something clean. And so by taking something that's sort of low tech, but ideal over that processing range, installing it before the electrochemical process, we're able to get something that was not just more acceptable to the users, but about 1/20th the amount of energy. Okay, let me transition to sort of why we want to, you know, everything's up to date was about the engineering and some, you know, advantages of bringing partnerships together to solve engineering challenges. This is actually a lot more important. About a year before we installed our first system in the field, we went out and we started talking to users. We would show them pictures, and we asked them, do you care about this? We said, you're going to recycle a liquid, you're going to reuse that, it's going to go into flush. What do you think about that? And that actually fed back into some of the engineering priorities, but we continue to do that as the systems go out into the field. And, you know, user insights is really understanding the interaction between the technology and the user, and how that impacts their decisions going forward. How does their interaction with the technology affect their willingness to accept that technology if it were to come in there? How is their perception changed after they've used it? All of these we care about as we start not just developing the engineering solution, but designing the interface with the user itself. And so again, remember my user insights and the 3 legs of the stool. If any 3 of these go out of balance, if they can't afford it, if there are local politics that we don't understand, if there are cultural, religious biases that we're not sensitive to, if any one of these fail, it doesn't matter if the engineering is successful. And so we have a host of partners that we work with. Most importantly, from the very beginning, it's been SEWA, Self-Employed Women's Association. If we want to develop something, a solution that's aimed at addressing the needs of women and girls, you can't have people that look like me going into a community and asking women and girls about their sanitation preferences. And so we work with SEWA and their local advocates to develop that. They already have a good rapport with the communities, but we also use them as an interface between sort of our engineering team and the communities themselves. And so we took a sort of multi-pronged approach. We did a 1,200 household survey where we just casted a broad net and say, what do you think about these broader issues? And then we conducted almost 100 focus groups, and those are 8 to 10 people in a room, moderated with a SEWA representative in each of those discussions, where we want to dive deeper into, what do you think about these issues, so you can understand how much they care, and you end up with sort of a progressive discussion. And then we ask people after they've used it, what do you think? And all of those combined, they have different kinds of data, but all of those combined help us to develop a better product, so that next year when it goes out into the field, we're still expecting some issues, but we're hoping that a lot of things we've addressed along the way. A lot of discussion around water reuse. India is more of a squat and rinse society, so no toilet paper. They use the water to rinse. And so how do you feel about that, knowing that it's gone through a recycling or a reuse process, where what you're using to flush with has been processed from someone else, especially if it's a community toilet. And so there was a lot of discussion around water reuse, what extent, if it's a family toilet, acceptance might be a little higher. If it's a community toilet or totally public toilet, less so. None of these were not unexpected, but what was important to us is we were worried that it was going to be a showstopper around water reuse. And there's still some concerns, there's things we have to do, but remember those different combinations of liquids. If you have something that looks like this, these issues are going to be a lot stronger. The perception, the experience with, if you're seeing something flush that looks like this, you're much more and smells a little bit like there's some residual chlorine, you're much more likely to accept the new technology and the concept of water reuse. So the engineering significantly impacts the user experience, and then that then drives the priorities around the engineering. We actually put a crash team when we were having a lot of the feedback from this. We actually put a team together to focus on, okay, how do we deal with the color? How do we deal with the odor? We have to deal with that. And then, okay, lessons learned, not unexpected, color, odor makes a difference. Doesn't matter. You can tell them it's disinfectant, you can tell them it's safe, it doesn't matter. What does it look like? What does it feel like? What does it smell like? The presence of chlorine was good. And then further, moving forward, the issue of having that or maintaining that and keeping that sort of polished water look is really important. Okay. Good, we're getting close. Next one is just when we talk about opportunities to collaborate. And Randy and I have talked about this, and I think across the portfolio, any legs of the stool, including the engineering leg itself, there are opportunities. we're looking for students, we're looking for teams, we're looking for faculty who are interested on the policy side. interested in developing innovative business models. We had a team last semester look at what we called the entrepreneurial ecosystem around toilets and sanitation solutions aimed at women and girls. So if you're trying to develop a new product and you're trying to attract women and girls, how do you create a broader ecosystem around that product? So you have this fancy new toilet you're plopping down. You want to create a business around that. What other businesses or what other adjacent services, products, consumables could exist that will lower the overall risk profile for that, looking at the ecosystem? And then, understanding the cultural, the social priorities around adoption are really important, and they vary tremendously. Family priorities, prior bias. In some cases, educational campaigns will make a difference. Other cases, you actually need to fit into their existing bias and figure out how to do that. This is one that came up recently, and it was posed to us. It said, okay, now you're creating this disruptive technology. You're going in and you're changing the way people are processing waste in these communities. What's the impact of a new Reinvent the Toilet technology on the energy-water nexus in developing countries? How will a toilet network of 1,000 new toilets in a community impact climate change, for example? Should it? Will it? What's the impact of off-grid sanitation solutions on the local power grid and the power demand? In a system like ours, we're drying the solid waste and we're burning it. What's the impact of that? Now we have that fecal waste that's now being burnt. So instead of it ending up in a liquid stream, we're burning that. What does that do to the local emissions profile and the air quality? So let's just kind of look at that and say, okay, let's look at a community and say, okay, what would happen if we then took all of that solid waste and we burned it? Average person produces about 124 grams of feces per day. There's pretty wide bars on that, but it's a good ballpark. It's about 324 billion kilograms per year if you look at the whole human race. Just for fun, let's just look at, if we take all of the feces that's generated each year and then ran it through a process similar to ours, feces is about 75% water. I like that number because it gives me around about 100 billion kilograms of dried biomass that we can burn, right? I want to think about that. What happens when we burn that? Okay, let's look at greenhouse emissions. Automobiles produce about 1,500 million metric tons of greenhouse emissions per year. They represent about 14 to 15% of the total. So you have about 10 billion metric tons of greenhouse emissions each year. Your 100 billion kilograms of feces, that's about 100 metric tons. It represents about 1% of the global greenhouse gas emissions. What do you think? Is it significant? What are the broader impacts? Don't know. So those are some of the things that we want to ask ourselves, we want to look at, we want to model it in the communities. What happens if we take those systems and they're going to be concentrated in some of the lower income communities? What do we think about now having a whole bunch of feces combustion systems in just the low income communities? And then how do we model that and how does it impact the overall air quality? Okay, this is our team at Duke. I'm very excited. We had a retreat last week, so so this is an updated photo. This is one of our sites in Ahmedabad, outside of Gujarat. That it's one of our potential test sites in Ahmedabad, but it's also been one of the communities that we've done a lot of focus groups around water reuse, acceptance, etc. Thank you.